stands for high frequency of recombination. Good way to remember it, HFR. Okay, so now we still have a highly functional F plus cell behaving just like an F plus cell. Has all the genetic information of an F plus cell, but it's got its F factor incorporated into the chromosome. So someone want to, feel free to cheat and look off the slide. Someone want to tell me, why do we call this high frequency recombination?
It replicates with the cell itself.
Replicates with the cell itself, you're right, and then what else is it going to do? Think beyond that. Think of accidents. Anyone want to guess?
Mutation.
A little bit. It's a form of genetic variation, yes. What's going to happen is, when this guy goes to replicate this F factor, so say he does extend the sex pilus over this guy, okay? So let's say he does extend the sex pilus over, and he has to replicate that F factor, remember? When he replicates that F factor, he may not cut and paste in the perfect way, okay? Not the pasting, but the cutting part. So you may end up cutting part of it. And so you're going to take, not just, I wish I had two different colors. You're not just going to take F factors, you're also going to take host chromosome 2. Going back to the high frequency of recombination. Not only are you recombining the cell by giving an F factor, you're recombining the cell by giving it chromosomal DNA as well. Alright, so let's go through this cartoon. So here you have an F plus cell. Okay, for right now, don't worry about these markers. I'll tell you about those markers in just a second. Here you have an F plus cell, and then you have an F factor. Okay, so it's a nice F plus cell. It has its plasmid, has its chromosome. All right, it becomes an HFR cell when that F plasmid gets stuck into the host chromosome. Let me just show you. Okay. So what can happen is the F plus cell is going to go through what F plus cells do, and they're going to create a sex pilus, and they're going to reach out and touch an F minus cell. Okay? And it's going to start to replicate that little strand of F plasmid information that's chromosomal. But when it does, you see that little red strand going through. But when it does, it's also very likely going to take a little chromosomal information with it. Okay? And so it's going to send that on through. So now you're going to end up with F plus cells again, but you're going to take a lot of chromosome with it as well. All right. So is everyone comfortable with that? Some nodding. Okay, let me explain what these markers are. So, what these markers are showing you is that, in this case, your recipient cell is negative for the gene pro, I don't know, and negative for lac minus, from degradation of lactose. All right, so it's negative, the recipient cell is negative for those genes. All right, your F plus cell, your HFR cell, because it's incorporated, is positive for those genes.
Yes, totally.
So what you can do is, as it replicates and sends down into the recipient cell, if it's been bound for a long time, and they can manipulate this in the lab, you can manipulate conditions in the lab such that cells are in contact, in mating position, if you use that word, in contact with each other for 10 minutes, maybe only one gene goes through. If they're in that position, say for 20 minutes, more genes go through. So the longer they're in contact with each other, more information goes through. All right? And the reason I tell you that next level of complexity is this is something that's really heavily used in molecular biology labs. This is a tool. You can manipulate how much gene they get just by attaching an F factor to it and sending it over into another cell. Okay? And then keeping them bound for so long. All right? The take-home message is in HFR conjugation, you have an HFR cell that has an F factor and some chromosomes.
Yes.
And it sends it over to the F minus cell. And now that F minus cell becomes F plus. But very likely in many conditions, depending on how long and depending on what got sent where and when, you can end up being HFR or not. All right? Because the recipient cell can also end up being HFR if the strand that goes through, then incorporates into its own chromosome, right? Anytime you have an F plasmid incorporated into a chromosome, you have an HFR cell. I'm seeing some happy nodding and a little bit of snoozing. Everybody cool? Yeah, Mike.
So is the amount of host chromosome that goes through only dependent on time? Like if you left it long enough, would the whole thing transfer over?
In theory,
Okay.
but it's obviously not that simple. Yeah, yeah, in theory, but theory. Alright, okay, so let's shift gears. Transformation, much easier to digest. So transformation is just the ability of a bacterial cell or an archaeal cell to take up free DNA from the environment. And think about it, an environment, certainly if you're in a laboratory setting where you have, cells growing in a tube in a contained little ecosystem there with a finite amount of nutrients, you're gonna have a lot of cell death, cell breakdown, et cetera, and they're gonna scavenge resources from the environment. Alright, and so they're gonna very comfortably wanna take up DNA from the environment. And so in some cases that DNA gets taken up and it gets incorporated into the recipient cell, took it up freely from the environment, and then you end up with a stable transformation of recombinant. Okay, in some cases it gets degraded, as I showed you before, maybe restriction enzymes, and they just scavenge the nucleotides from it. Alright, and so that's in the case of a linear piece of DNA, but absolutely they can take up plasmids too. So when you clone in a laboratory, what you do is you'll actually just order it for one of my students. You'll order a kit that'll sell you a DNA plasmid. You can put your gene into that DNA plasmid, and then you can get what you have we call competent cells. Competent cells are cells that have really loose and free and willing to take up free DNA from any situation. Put them with a little bit of food on a shaker, make it nice and warm and happy, and they'll take up that plasmid, and then you end up with a recombinant that's recombined the way you wanted it to be recombined. So this is a process that occurs very naturally in the environment all of the time, in the naturally occurring environment. But in a lab, we can manipulate it and control it and use it to our will. Not as sexual as it sounds. Alright, so this is transformation. Just the free uptake of DNA, pretty easy to digest. Alright. Okay, oh, and then just going back to the lab idea, because this is something you could very easily end up doing in a lab before you're done with this degree. So in this case, we'll put a marker on it. So in this case, we have this cell, this competent cell, that's going to take up that little piece of DNA that we want it to be transformed with that piece of DNA. And then you'll put something like a marker on your vector, on your piece of DNA you want to send in. The vector is the piece of DNA you want to send in. Alright, so in this case, we know our recipient cell is lac minus, can't grade lactose, but we'll put a lac plus marker on our piece of DNA that we want to have transformed. So basically you'll, create this nice soup of media and conditions and nice temperature, and then the cell will freely take it in. It will just take in that piece. And then when it recombines, you've had successful recombination because the DNA that you wanted to transform has a lac plus marker, whereas this was lac minus. So now we've created a recombinant, it's recombined and put that DNA into its own chromosome that we transformed into the cell, and now it's lac plus. So now all I have to do is grow these cells on media where the only sugar is what? Lactose. I can grow these cells on the media that only has lactose, and then I know I've got my transformants. And I know I've got the recombinants. It's a nice, easy little test. Alright, so let's switch to transduction, and then we'll wrap up, and you guys get to go early today. Okay. So transduction is the transfer of bacterial genes via a phage. And let me remind you of something. Okay, hopefully this looks abundantly familiar. So remember we talked about the lytic and the lysogenic stage of the phage. And feel free to cheat and look at the slide. What is the lytic stage? What is the lytic cycle?
It's the active cycle where it's constantly replicated.
It replicates immediately. Okay. Destructive. Okay, good word. Alright, absolutely. The phage inserts this chromosome in there. It uses the cell's hardware to immediately make a bunch more prophage explode and go out into the environment and go infect new cells, lytically. All right, someone tell me what lysogenic is.
So pretty much dormant stage, it'll go in, insert its DNA into the cell's DNA.
Yeah.
And that'll replicate throughout time, and that cell will replicate that DNA, and it goes on and on until something triggers it.
But something triggers it to lyse the cell and go lytic, absolutely. But in the process, it forms what we call a prophage. And the prophage is where you have phage DNA incorporated into the chromosome of the cell, and it's being replicated. All right. In transduction, think about this lysogenic cycle. In transduction, every time the cell replicates itself, it's taking that chromosome with it, replicating that phage DNA. But then what happens when it wants to go lytic? When it wants to go lytic, in this little picture, it very nicely excises perfectly phage chromosome from its own chromosome, makes new phage particles, and they all explode. So you'll see this here, the phage DNA is red. All of the little phages that are gonna go lytic and explode only have red DNA. But can you imagine a situation where when the prophage basically leaves and excises itself from the host chromosome, it takes host DNA with it. And that can easily happen. They don't always cut perfectly. And so if they take host chromosome, you may have a phage exploding that, say, took all red DNA, perfect, fine, but maybe one that took some red and some blue. All right, you even have cases where they take some blue. So, take all blue. So, what you're doing is creating a phage that's going out into the world to go reinfect other cells that now has bacterial DNA in it as well as just phage DNA. And then that's going to create a recombinant when that phage goes and bites into a new cell. And we call this transduction. So here you have a case where you have a phage that's attacking the cell with the chromosome. The phage DNA is red, notice. It gets into the cell. All right. It's about to go lytic. When it goes lytic, basically all of the DNA gets cut up. Some of the phages are formed with the red phage DNA. Some of the phages are formed with blue DNA from the host chromosome. All right. And in this case, they're genetically engineering it, so they put nice little markers on there and they can see how much transduction actually happened. But the point being is that these phages are released out into the environment. Some of them with blue DNA, some of them with red DNA. Some of them with host DNA, some of them with just phage DNA, maybe some of them with both. That phage is going to go infect a new cell. All right. And when it goes infect a new cell, then it's going to become a prophage again, etc. This is going to end up getting cut up again, etc. And the cycle continues. So it's movement of host or bacterial chromosomal DNA from cell to cell to cell via phage infection. All right, questions? Okay, so this is, I'm glad, not too long of a lecture, but a very important lecture. Really important concepts. I promise you'll see them on a test. Yes.
Can you repeat the definition for transduction?
Transduction is movement of bacterial or heel host DNA via a phage from cell to cell. So one phage attaches to one cell, and when it goes lytic and leaves, it takes some of that host DNA with it. It goes and bites a new cell, it transfers it to the new cell, creating a recombinant. And in this case, they were able to track that because it had markers on it, like histidine and lysine positive, and they transferred it to a cell. In this case, it was histidine and lysine negative. So when the phage inserted this new DNA, it became a stable recombinant and we can test for that. Yeah.
You said it's possible that it could be all bacterial DNA?
Yeah, I know, and I'm always mystified by that.
So
I
would,
need to talk to Sandra Atkins about that.
so would that prophage even be able to go lytic?
How does it even function? I know. Yeah, I'm interested in that. How does it, because if it's only got this DNA, then how is it gonna make new phage particles?
Yeah.
Exactly. So in this case, in the case of this cartoon, and maybe it doesn't, so maybe that's just an engineered thing in the lab. Whereas in the case of this cartoon, they're just using it, they're gonna transfer one sequence, and then they know it lands over here. This one excises, it can go out and infect, but it's non-reproductive.
Okay.
Okay, but I'm sure the red ones can still reproduce, and I'm sure there's plenty of cases out in the environment, billions and trillions and natural biological sense. This little image here is transduction in the sense of engineered. All right, everybody okay? We've got tons of time for questions.